Hello everyone. So in the previous session we have discussed the concept of power series where I have already told you that power series will be an expression of the form summation n is equal to 0 to infinity an into z minus a power of n. Right? Now while explaining the properties of the coefficients, complex number coefficients of a power series, I have told you that suppose if a is equal to 0, then this power series reduces to n is equal to 0 to infinity an into z power of n. Right? Now based on this concept, let us discuss the one more important concept called radius of convergence. It is very important. It is asked in one of the year. Define radius of convergence. Radius of convergence of a power series. So radius of convergence of a power series. Meaning is, suppose if I have a power series, say n is equal to 0 to infinity, particular case, that is an into z power of n is a power series which is in terms of z. Now let us consider r as 1 is equal to a, where a is given by limit supremum and limit infimum. I have told you in the previous session, please go through that. Where if a is equal to limit supremum of an power 1 by n. Let me define once again. Suppose if a is equal to limit supremum of magnitude of an whole power of 1 by n and r is equal to 1 by a, then r is called as radius of convergent of a power series. Fine. Let me define once again. Let us consider a power series summation n is equal to 0 to infinity an into z power of n, which is a power series in terms of z. Now, if a is equal to limit supremum of all those values of sequence an whole power of 1 by n, then r is equal to 1 by a. So, r is called as radius of convergence of a power series. Fine. And one more thing you have to remember, that if magnitude of z is less than r, then the disk of convergence of this is the disk. As I already told you in the beginning introduction session of a complex analysis, that if mod z is less than r, we can say it is a disk of a power series. And moreover, circle equation is mod z is equal to r. I have already told you all these concepts. Fine. You just need to remember those concepts. Fine. Now let us prove the theorem based on this radius of convergence of a power series. So here is a theorem statement. So this is a theorem on radius of convergence of a power series. Let summation n is equal to 0 to infinity an into z power of n is a power series, and a is limit supremum of an 1 by n and r is equal to 1 by a. That is, this is the definition of radius of convergence. Then we have to prove that if a lies between 0 infinity and r lies between 0 to infinity holds, and the power series converges for all z, that is with mod z less than r, then the series is diverges for mod z greater than r. In the sense, if mod z is less than r, we have to prove the series is convergent. If mod z greater than r, we have to prove the series is divergent. Fine. And the second one, if a is equal to 0, then r is equal to infinity, then the power series converges. Third one, we have to prove if a is equal to infinity and r is equal to 0, the radius of convergence is diverges. These statements will be useful for solving problems. You have to remember, if a is equal to 0 and r is equal to infinity, the power series, that is radius of convergence, is converges. If a is infinity and r is equal to 0, radius of convergence is diverges. And if r lies between 0 and infinity, the series converges uniformly in the disk. Mod z is less than or equal to rho. So this is the disk equation, where rho lies between 0 and the radius r. So we have to prove this. First let me prove the first statement. Fine. So what is the given data in the first statement? Given that a lies between 0 and infinity and r lies between 0 and infinity. Right? And moreover, as per the definition of as per the given statement, we can write r is equal to 1 by a. Now let us consider a complex number in a complex plane C. Fine. Clearly mod z will be less than any real number. Why? Because complex number is always less than a real number, as it contains imaginary plane. So it is entered different concept. So mod z is always less than r. Now mod z is less than r can be replaced by 1 by a as it is given in the statement. Now let me choose a small arbitrary number, say epsilon, in such a way that mod z is less than 1 by a plus epsilon. Meaning is, suppose if some value is less than 1 by 2, if 1 by 2 in the sense it is less than 0.5, then if you are adding some small quantity, say 1, 2 plus 1 is 1 by 3. So we are dividing it in further. So it will be obviously less than that value also. Right? So you can, if you want, you can calculate, right? If the certain value is less than 1 by 2, it will be less than 1 by 3 also. Similarly, here mod z is less than 1 by a. Since we are adding some more quantity to epsilon, in the sense we are dividing 1 into, suppose if a is equal to 2 here. So we are dividing 1 into 2 parts. Here, epsilon is equal to 1 in the sense we are dividing 1 into 3 parts, which is smaller. 1 dividing 3 is smaller, right? So if it is 1 is dividing 2, if this value is less than 1 by 2, then this value will be less than 1 by a plus epsilon. So throughout the complex analysis, it is just an abstract and logic you have to understand. Fine. Now I can write this as a plus epsilon into mod z is less than 1. I have just cross multiplied it. Fine. Then choose an epsilon greater than, positive quantity epsilon, and there exists an integer n naught which is belonging to n, such that magnitude of an whole power of n will be less than a plus epsilon. This is as per the definition of convergence. Fine. This is as per, what is the definition of convergence says, that is magnitude of an whole power of 1 by n minus a is less than epsilon. Whenever an power of 1 by n is converging to a, this is a given statement, in the given theorem statement itself it is given. Right? So this is converging, meaning of convergence. So I have considered the concept of convergence, definition of convergence, and I have shifted this. An power of 1 by n is less than a plus epsilon. Fine? That is how the concept is. Now, let me take sum over the element, or else let me write here. Let us consider magnitude of summation of an into z power of n. That is some magnitude of a given power series I am going to consider. N is equal to 0 to infinity zn. Now I can write this as, since I am splitting the magnitude, I can write this as less than or equal to summation n is equal to 0 to infinity. I am going to split the magnitude inside. So I can write an. This is as per the properties of mod or magnitude. Right? We can write like this. Now what I have assumed is an. See here. As an power of 1 by n is less than a plus epsilon, I can write this as, if you want I'll just show you here. See here, what I have, an power of 1 by n is less than a plus epsilon, right? So I can write an as rising power n on both sides. I can write this as a plus epsilon power of n. So I can, with this, I can write the above statement as, see here, I have considered this. Now I can write, I'll just continue here. Let me write LHS as it is. N is equal to 0 to infinity an into z power of n, which is less than or equal to summation n is equal to 0 to infinity. Now you can note that magnitude of, from this equation, magnitude of an can be written as a plus epsilon power of n. So let me do it. A plus epsilon power of n mod z power of n I'll keep as it is. Fine. Now let me take t as a plus epsilon into mod z. Fine. So I am going to write this as n. Just I have assumed one of the variable, that's all. I can write this as t power of n. Whatever the variable I have in the base, I have taken that as t. Obviously this value will be less than 1. Why? Because epsilon is very arbitrary, and when you are going to take magnitude for z, you will get less than 1. Product with that, you will get, obviously it is less than 1. So with this I can write magnitude of n is equal to 0 to infinity an into z power of n will be less than or equal to summation n is equal to 0 to infinity t power of n. Now this is of a form geometric series. While explaining the concept of power series, I have told you the properties of a number a naughts. You just go through that video, then you will understand. This is the geometric series, right? And the common ratio is less than 1. Right? Why? Because when you're going to take multiplication, elements of this t will be of form this. So if you're going to write one more element, since this element is less than 1, when you're going to take difference of those two elements, again it will be less than 1. Fine. So as I already told you, when the term, when the difference is less than 1, then the series will be convergent as per the properties of a power series I have told you in the previous session. Please go through that. So whenever we have in a geometric series, when a common ratio is less than 1, we can say this series is convergent. Therefore, I can write summation n. If this series is convergent, we can say this is also convergent. N is equal to 0 to infinity an into z power of n is convergent. Or else I can write, this is absolute value, right? So or else I can write n is equal to 0 to infinity an z power of n is absolutely, since I am removing the symbol, I am writing it in sentence form. Absolutely convergent, right? So convergent is same as absolutely convergent. Why? Because we have an absolute value here, so I have removed that and I have written it as absolutely convergent. Now let me take one value, say z, which is in a complex plane. As usual, in a complex plane, elements will be of the form z. So if mod z is greater than r, then I can write, since I have done this case for mod z less than r, now I am going to prove the second case, that is for mod z greater than r. I can write mod z is greater than 1 by a. Why? Because the value of r, it is given as 1 by a, so that is why I have written it as 1 by a. Now similarly, let me choose whatever I have done the concept, I am repeating the same. Now let me choose an arbitrary value epsilon. That is what I have done here also. So if that was the case, I can write mod z is greater than 1 by a plus epsilon. Now cross multiplication will give you a plus epsilon. I'm sorry, when it is less than, you are going to add epsilon. So when I am taking it is greater than, that is reverse, so you have to subtract it. I'm repeating once again. Since what I have chosen here is mod z is less than r, so I have added epsilon here. Since I have chosen mod z is greater than r, so I am going to subtract epsilon here. Fine. So epsilon, a minus epsilon will be less than, greater than 1. A minus epsilon is greater than 1. Right? Now we can also write that limit supremum of all the sequence an 1 by n as a. This is already I have explained in the previous session. While explaining the concept of, that is, limit supremum and limit infimum, I have told you this concept clearly. Please go through the first video of this lesson, then only you will understand this concept. While explaining the limit supremum and limit infimum, I have told you this concept clearly. See here, this is the page of the first video where I have written equation 3, a as limit supremum of xn. Here the sequence is xn, but in this theorem it is an power of 1 by n. So I have taken this as a. Now as per the definition, let me choose an epsilon greater than 0 such that there exists a number n naught belongs to n. Then I can write, as per the definition of limit superior, an power of 1 by n will be greater than a minus epsilon. I have already told you while explaining the concept. See here, I will just show you for your reference. Limit superior concept, first property I am going to use. Fine. First property, as per the second property I have written here. See here, xn is a sequence, then I can write a minus epsilon. Here an power of 1 by is a sequence, so I can write a minus epsilon. I have applied the limit superior definitions. I'm sorry, each and every steps I cannot explain in detail. So you have to remember previous session definition, then only you can understand well. Fine. So I have applied the properties of, definition of limit superior here. Now let me consider what I'm trying to prove is, first statement, we are going to prove that if a is in between 0 infinity, r is in between 0 infinity, then if mod z is less than 0, the series is divergent. So we are going to prove the given series is divergent. In the sense, we have to prove that given series is an into z power of n will not converge to 0. That is the meaning of divergent, right? So we have to prove that the given series n into z power of n is not converging to 0. So that is why we are doing all these things. Now let me consider a given power series. It is given by n is equal to 0 to infinity an into z power of n. Now as I can split this as see here, I'll just going to split this, n is equal to 0 to infinity. And one more thing is that in case of power series, if you want, you can change, otherwise you can rewrite as per the requirement of the theorem, an into z power of n. Fine. Now since we are talking about supremum, right? So an is what we have assumed an as in the second case. Somewhere I have written, see here, since mod an whole power of 1 by is greater than a minus epsilon, right? So I can write magnitude of an is greater than a minus epsilon power of n, right? Raise power on n on both sides, so you will get this. Clear? With that, I can write this as, which is greater than equal to, why? Because this value is greater than equal to n is equal to 0 to infinity a minus epsilon power of n into mod z power of n. So as we done in the first case, that is what we have done in the first case also. So let me take this entire base as t. So here also I am going to take entire base as t. So let me write this as summation n is equal to 0 to infinity t power of n. Let me write LHS n is equal to 0 to infinity an into z power of n, where t is equal to a minus epsilon into mod z. And moreover, it is greater than 1 in this case. Why? Because we have chosen mod z is less than r. So that is the reason t will be also less than r. Here I have chosen mod z is greater than r for the second case. Fine. For the second case. So that is why t is also greater than 1. Fine. Now this is a geometric series as I already told you. With common ratio is greater than 1. T represent a common ratio. In the first case common ratio is less than 1. So it is absolutely convergent. But what we have to prove is it is divergent. We have to prove that it for greater than 1 it is diverging. Right. So if this value is greater than 1, I mean what we can say is a common ratio. T is a common ratio whose value is greater than 1. Meaning is that I'll just write here. Therefore, an into z power of n will not converge to 0. Since it is greater than 1 or it is less than 1, but it cannot be equal to 0. It is not converging in both the cases. See here. First case I have chosen mod z as less than r. Only possible case is mod z is greater than r. It cannot be equal to radius of convergence. If the sequence is equal to radius of convergence, then there is nothing to prove. Right? So in the first case it is greater than less than 1. So in the second case it is greater than 1. That is common difference of a sequence is greater than 1. So it is not converging to 0. So meaning is that it is diverging as n tending to infinity. I'll just write a statement here. So let me write here. Therefore, summation just write here. Wait. So therefore, I can write this as summation n is equal to 0 to infinity. An into z power of n is divergent. Right. So in the first case, I'll just repeat once again. First case I have chosen that mod z is less than r, for which I have obtained a common difference t as less than 1. Right. So it is absolutely convergent. In the second case I have chosen mod z is greater than 1, greater than r. Therefore common ratio is also greater than 1. Meaning is that the series is not converging exactly. So it is divergent. So that is what I have written here. Therefore the given series an into z power of n is divergent. And that is the proof of the first one. Right. That is what we need to prove is the series is divergent. Hence the proof of first one. Hope so it is clear. Right. Now let me prove the second one. Second one is if a is equal to 0 and r is equal to infinity, we have to prove that this sequence is convergent. Right. That is we have to prove that the common series is less than 1. Or it is less than 1, meaning is it is absolutely convergent. Absolutely convergent is equivalent as convergent. Either we can prove it is absolutely convergent or convergent. Anyhow, it should be converges. That's all, right? So let me prove the second one. I'll just prove here. Second one. Right? Now, let me write the given data for the second one. What is the given data? You can clearly see here. A is equal to 0. Given A is equal to 0 and R is equal to infinity. Right? Now we know that the power series an into z power of n, that is n is equal to 0 to infinity an into z power of n is convergent. Right? We have to prove this. To prove that given is a is equal to 0 and r is equal to infinity, we have to prove an into z power of n is convergent. Now let me consider the definition of limit superior and limit inferior, as I already explained this in the previous session. So limit superior of a sequence an whole power of 1 by n, as let me take this as a. This implies that limit superior of, if you want you can write LT or LIM, both are same. an power of 1 by n will be equal to 0. Why? Because the value of a is 0. I have just substituted it. Fine. Now for a given epsilon greater than 0, there exists a n naught greater than, n naught in a set of integer n, such that magnitude of an power of 1 by n will be less than epsilon for n greater than or equal to n naught. As per the definition of limit, I have chosen this. If limit this value is equal to 0, the meaning is convergence. So convergence of the sequence, I am going to consider the definition of a limit. So epsilon greater than 0, there exists an integer n naught belongs to n such that magnitude of an power of 1 by n will be less than epsilon. Now let me consider a given series, that is n is equal to 0 to infinity an into z power of n. Right? Now we can write this as summation n is equal to 0. I am going to split inside an into magnitude of z power of n. Now as I already chosen that an, if an power of 1 by n is less than epsilon, I can write magnitude of an is less than epsilon power of n, right, rising power n. So that I can write the first term as summation n is equal to 0 to infinity epsilon power of n into mod z power of n. With this, I can write magnitude of n is equal to 0 to infinity. Let me take the base value, since power is same, I can take base value as t, right, where t is equal to epsilon into mod z. And obviously it will be less than 1. So let me write LHS as it is, summation n is equal to 0 to infinity an into z power of n. Fine. This is obviously a geometric series, as I already told you while explaining the concept of power series. So this is a geometric series. The common ratio is less than 1. So as I already said, when in a geometric series, if the common ratio is less than 1, the series is convergent, right? This implies magnitude of n is equal to 0 to infinity an into z power of n is convergent. Implies that it is convergent, meaning is absolutely convergent, right? Why? Because we have it absolute value here, absolutely convergent. If it is absolutely convergent, we can say it is convergent. An is, just by removing the absolute sign, I have written this is convergent. Fine. Absolute convergence, I have written it in a sentence format. So I have removed the symbol, so I can write the term which is inside the absolute value is convergent. So that is what we require to prove is, look at the second statement. If a is equal to 0 and r is equal to infinity, we need to prove n is equal to 0 to infinity an into z power of n is converges. Hope so it is clear. So second one proof completes. Now let me prove the third one following the same procedure, but we have to take a value as infinity and r is equal to 0. So let me prove here. So whatever I have done for the second one, I am going to use the same to prove the third one. So let me prove third one just by following the second one. Why? Because it will be easy for you to practice. So third one, look at the statement. What is the given data? First write the given data. Given a is equal to infinity and r is equal to 0. What we have to prove is, to prove that summation n is equal to 0 to infinity an into z power of n is diverging. Diverges. So this is what we require to prove is. Now what we have done in the second case, let me follow the same. First we have to assume, that is, let limit supremum of summation magnitude of an 1 by n as a. Right? Now here what is the value of a in the second case? It is 0. So that is why I have substituted 0. Here the a value is infinity. So let me substitute as infinity. Limit supremum an power of 1 by n is equal to infinity. Now I have considered the definition of what we say, this limit definition, right? If for every epsilon greater than 0 and for any integer n belongs to n, we can write magnitude of n power of 1 by n less than epsilon convergent. Now whenever you have divergent, this symbol greater than or equal to will become less than or equal to. So same step I am going to write. Why I am showing this is, it will make easy to practice. N naught belongs to n such that magnitude of an whole power of n less than epsilon for all n less than or equal to n naught. Why? Because we are proving it for divergent case. Fine. Just have written the same. Now let me consider the same value. Let us consider magnitude of n is equal to 0 to infinity an z power of n. Now let me split this so that you will get n is equal to 0 to infinity magnitude of an magnitude of zn. Right? Now from this I have to replace, that is, if magnitude of an whole power of n is less than epsilon, I can write magnitude of an as epsilon power of n. So I can replace this value as, here the only changes here is, since we are proving this for convergence, so you will get less than here. Now we are proving it for divergence. So whenever you have divergent, all the symbols will be changing. That is, less than will become greater than. Here greater than will become less than. Remember, for convergence and divergence, in the definition, less than will become greater than. Similarly, greater than will become less than. So that is why I have written greater than here. So an will also become greater than epsilon power n. So I can write this an value as less than will become greater than epsilon power of n. Let me write summation n is equal to 0 to infinity epsilon power of n into mod z power of n. This is what I have. Now basis we have to take it as t. Let me write LHS as it is. N is equal to 0 to infinity an z power of n, which is greater than summation n is equal to 0 to infinity t power of n, where t is equal to epsilon into mod z. That is what we have done in the second case also. See here, the same thing we have to follow, only sign will be changing. Now this value is less than 1 for convergence case, since it is greater than 1 for divergence case. That's all. So from the, since the common difference in the common ratio is greater than 1, hence you have to write the statement. Anyhow, I'll send you the notes, and I'm just not writing all those statements here. Since this geometric series is with the common ratio greater than 1, therefore it is divergent. That is, an z power of n will not be converging to 0 as n tending to infinity. Therefore, the given series n is equal to 0 to infinity an into z power of n is divergent. Not divergent in the sense it is not converging to 0. So that's all. That is what we need to prove is. You have to follow the same step as for second proof. So this is the third one, right? When a is equal to infinity, we have to prove that this series is divergent, and we have proved that the series is divergent. Fine. Now the last one proof, if r lies between 0 and infinity, the series converges uniformly in the disk. Given disk equation is given, that is mod z is less than a rho, and r will be in between 0 and infinity, and a rho will be in between 0 and r. We have to prove that the series an into z power of n, given series an into z power of n is converges uniformly. So let me prove that. That is the fourth one, last statement of the given theorem. And before going to prove the fourth theorem, let me clarify. Uniformly convergent, anyhow, we have, whether it is uniformly convergent or pointwise convergent, we have to prove inside this disk the series is convergence. So let me prove the fourth one. Let me write the given data. Given, what is the given data in a fourth one? R lies between 0 and infinity, and the disk equation is given. It is given by d is equal to mod z less than or equal to rho, and moreover rho lies between 0 and r. This is the given data, right? Meaning is that rho is less than r, right? That is, rho will be less than r is the, what is the value of r given in the problem? R is equal, theorem, r is equal to 1 by a. So let me replace r by 1 by a. Right? Now choose an epsilon greater than 0, then rho will be less than 1 by a plus epsilon. Same procedure we are following that we have done for the previous case, right? Rho is less than 1 by a plus epsilon. Now with the cross multiplication, I can write a plus epsilon into rho is less than 1. Now let me take the definition of limit supremum. Whatever I have done for the previous case, that is first proof, I am going to do the same. See here, right? A plus epsilon mod z less than 1. Now I have taken limit supremum, second case, right? Let me show you. See here. This definition I have assumed, right? So I am going to assume the same definition of limit supremum. You have to remember all this definition each and every time. I cannot repeat it, right? Now as per this, I can write magnitude of an whole power of n by n will be less than a plus epsilon. This is from the second property of a supremum. Second property of supremum. As I already told you, I have done this in a first session. Please go through that. I cannot keep all the pages every time to show you. See here. In the first session, I have proved this property of supremum. I have used the first property. If xn is a sequence, as per the definition of supremum, a plus epsilon. This page is from the first session where I have explained the concept of limit supremum and limit inferior. So as per the limit superior, xn is less than a plus epsilon. So first property I have used here. Here the sequence is xn. Now what I have, in place of xn, what I have? An power of 1 by n. So that is why I have this statement. Clear? This is from the second property. Just for your reference I have written here. Now let me consider magnitude of n is equal to 0 to infinity an into z power of n. So we can split the magnitude inside. So I can write this as magnitude of an into magnitude of zn. Now an is, see here from this statement, an will be less than a plus epsilon power of n, rising power n. This statement will be written like this, right? So I can write this as less than or equal to summation n is equal to 0 to infinity. An is less than a plus epsilon power of n into mod z power of n. Now since powers are same, let me take base as t. Let t is equal to a plus epsilon into magnitude of z. So I can write this as n is equal to 0 to infinity t power of n. Let me write LHS as it is. N is equal to 0 to infinity a n z power of n. Right? Now we can clearly note that the common difference is less than 1. That is, common ratio is less than 1. Right? Why? Because we have assumed that it is less than r. That is less than 1 by a. So if that was the case, it is also, common ratio is also less than 1. So as I already told you, when the common ratio less than 1, given series is convergent. Therefore, the given series is convergent. You just write one more statement as per the given question. If it is convergent, obviously it will be uniformly convergent. Therefore, summation n is equal to 0 to infinity a n z power of n is uniformly convergent in the given disk, in the, what is the given disk equation? Mod z less than or equal to rho. In the given disk, mod z less than or equal to rho. So hence the proof of the fourth one. Hope so you understand this concept. So either they can ask all the 4 questions at a time, or they can split the theorem. So you have to practice well. Hope so whatever I have done in this session, it is clear for you. Notes will be forwarded in the group. Please copy the same. Thank you. Continue in the next session.